Good morning. My name is Anna Simmelson, and I want to welcome you to Tier 3 Chemistry. I provide chemistry tutoring via Skype, and a lot of times people are unclear as to how this whole thing works. So I decided to record a short video to demonstrate how the tutoring via Skype would work, what you would see on the screen when you're talking to me. So you'll be seeing me, but you also will be seeing this whiteboard. And what I decided to do today is to choose a concept from organic chemistry for demonstration and to explain to you how the tutoring works. So what we're going to be discussing today is the addition of HBr to alkenes. And I chose propene as an example of alkene. And if you just add HBr to this, you will obtain this product called 2-bromopropane. And notice that bromine ends up on the more substituted carbon. When I mean more substituted carbon, I mean between the two carbons that made up the double bond, the bromine ends up on the more substituted of the two. This type of product is called Markovnikov product, and it's named after a Russian chemist that discovered it. And by the way, his last name means carrot for ease of memorization. Now, however, if you take the same starting materials, but you also add a little bit of peroxide to the mix, namely catalytic amount, that means just a little bit, you will end up with 1-bromopropane. The bromine is going to end up on the less substituted carbon of the two that made up the double bond, and this type of product is called anti-Markovnikov product. The question is why that is the case and what exactly is going on here. So to answer this question, we're going to look at the mechanism of both reactions. So let me clean up the board now. So let's start with the first one with just addition of HBr to alkenes. So what we're going to have here is electrophilic addition. So the pi electrons that make up this double bond will be used to create a bond between one of the carbons and the proton of the HBr. So if we're going to do arrow pushing, then it will look like this. So we're going to destroy the hydrogen-bromine bond and form the new carbon-hydrogen bond. So now, let me just draw this first. So the hydrogen comes in here, and here we have a positive charge. So notice what happened. One of the carbons formed a bond between carbon and hydrogen, and the other one obtained a positive charge. Carbon with a positive charge is called carbocation. And as we know from previous chapters, the stability of a carbocation increases with increasing substitution. In other words, the more substituents you have, the more stable the carbocation is. This is a phenomenon known as hyperconjugation. Now, if we were to choose between these two carbons, we want the positive charge on a secondary carbon rather than primary. And so now, in this first step, not only did we form a bond between carbon and hydrogen, we also created an anion called Br-. So now the Br- will perform a nucleophilic attack on the carbocation and form a new bond, namely carbon-bromine. And so now this is how our product is formed. So hydrogen is here and Br is here. So this is Markovnikov product, right? The Markovnikov rule states that if you're adding something to alkene, the nucleophile will end up on the more substituted carbon. Okay, so now let's see what is going on when we have peroxides in the mixture. Now, let me clean the board again. Peroxides are very reactive species. And when they're exposed to heat or light, it depends on the peroxide that you're using, the following reaction takes place. So I will just denote these groups as R, because peroxides come in different flavors. So if we expose this to heat or light, this oxygen bond will break. But it will break in a very interesting fashion. What will happen is called homolytic cleavage, which means that it's sort of like an amicable divorce when two spouses divorce and they divide their property in equal parts. The same is happening here. Each of the participants will end up with one of the electrons that made up this bond. As a result, you will form species that have one unpaired electron. These species are called radicals. In this case, this is alkoxy radical, and they tend to be very reactive. What alkoxy radical really wants is to abstract hydrogen from something so that it can turn into an alcohol. Or if you're dealing with hydrogen peroxide, then it will turn into water. So what a better candidate for this than hydrogen bromide? So now, let's do this here. Okay, so now, when alkoxy radical adds to hydrogen bromide, the hydrogen-bromine bond will also break in a similar fashion that we observed here. In other words, we're going to form oxygen-hydrogen bond in a bromine radical. So notice also that here I'm using the single-headed arrows. These arrows denote the radical mechanism. So now we formed these two species. We formed the Br radical, right? And we also formed ROH, right? The alcohol, which we honestly don't care about, right? So now the Br radical, the bromine radical, will add to our alkene. So let me draw the alkene first. Okay, and so now the bromine radical will also add in the same fashion as we observed before. In other words, you're going to form two things. You're going to form carbon-bromine bond with one of the carbons, and you're going to form carbon radical on the other carbon that used to make up the double bond. So now let's see how that works out. So then the resulting intermediate is the following. CH2, CH radical, and then CH3. So now, the stability of radicals is the same as stability of carbocations. The more substitution on the carbon, the better. Again, the hyperconjugation phenomenon kicks in. So in other words, the bromine will end up to the terminal carbon of the double bond, so that it's the secondary carbon that becomes a radical rather than primary. Now, the carbon radical also wants to abstract hydrogen from someone, and it's going to abstract it from hydrogen bromide in the same radical fashion as we observed before. So now, let's actually do it that way. Okay, and so now we formed our desired product. Br CH2 CH3, and the hydrogen is here. And we also formed Br dot, which can now go back into the cycle and attack another molecule of starting material. So it's going back there. Okay, well, thank you for watching.